this is the last review topic we've got before your AP exam, and then I'm just basically going to open things up for you after that. So, it deals with magnetism and electromagnetic induction. We did several labs related to this. We did some simulations related to this with active physics. I'd encourage you to go back and look at those. At any rate, so these are the summary type things. Big ideas, magnetic fields. I don't know if that's the biggest idea, extend to infinity, but they do point from north to south outside of a magnet. In a magnet, they actually point from south to north, but that's not that important. The key thing is when outside of a magnet, they point from north to south. And anytime you have two magnetic fields interacting, where you would think of a north pole and a north pole, that creates a repulsive force. And when you have like a south pole and a south pole, that create a repulsive force, and a south pole and a north pole would create an attractive force. So, force on moving charges due to magnetic fields is from this formula, QVB. The direction of the magnetic force is given by a right-hand rule on a positive charge, left-hand rule on a negative charge. So it is not the same as the direction of the magnetic field. Magnetic force is always perpendicular to the moving charge's velocity. That is true. So the force is going to be perpendicular, or perpendicular to whatever component of that velocity is perpendicular to the magnetic field. Current carrying wires produce that. And when magnetic flux, which is basically magnetic field strength times area, through a conducting loop or square changes, you induce a voltage and you induce a current to oppose that change in flux. So these are the formulas on the AP sheet. Notice that these two are basically the same things. This just involves a vector direction. This is a version of Ampere's law. It's the magnetic field strength around a long straight wire. Magnetic flux, BA cos theta. The other way to think of, and this is the EMF generated. The N is for a solenoid or an inductor where you have a lot of different loops, but basically change in flux over change in time. So you could think of that also as, let's do this here, equals delta B A over delta T. So that's another way to think about that. This and this mean the same thing. So magnetic field strength is in Tesla. A is area, which is square meters, and seconds is time. So this is Tesla meters squared per second. Here, this would cause a voltage also when you have a wire moving in a magnetic field, which basically changes the area enclosed. This is Tesla times meters per second. That's Tesla squared meters per second. Same thing as up here. So that's actually pretty useful. Bar magnets posted something like this. Should probably make that, I guess I don't need to make that wider. So there's the example of magnetic fields lines. So they continue in complete loops. And like I said, outside the loop, they always point from north to south. But notice in here, they point from south to north. Now, they didn't draw those arrows, but I don't think you're going to be asked about that. North to south is a good way to think about it. Here they drew the arrows. Magnetic fields into the page, magnetic fields out of a page. Sometimes you'll see that as velocity or force also. So anything into the page or X's out of the page or dots. But usually we think about that as magnetic field strength. Dipoles I don't think are going to be things that are going to be asked about that much. This one, let's go ahead and talk about. Sorry, get my formula sheet out. Okay, so around a wire, if you have conventional current, which are positively charged, you can figure out the direction of the magnetic field with the right-hand rule. And I'm going to call this the curvy right-hand rule. So your fingers curve around like that. So if we are looking at this end where the current's coming out here, that is a dot, and the magnetic fields are going, in this case, counterclockwise. So make the dot your thumb and your finger should point counterclockwise. It's stronger closer to this and weaker further away according to this formula right here. So this is something on your formula sheet. That's vacuum permeability. That is 4 pi times 10 to the negative 7th, which is a little bit weird. And 2 pi r, and this is the current. So going back to this then, here, if we were looking at current going up this page, and we curved our fingers around, like our thumb is basically the current, so I'm doing that right now even though you can't see me, then my fingers point out of the page on the left side, into the page on the right side. That's why we have these as X's, and these are dots. I would use terms into the page and out of the page instead of X's and dots on your AP exam. So they talk about this. So if we had a wire going like this in a complete circle, then if I look at that, I have the magnetic field coming out of the page inside the circle, and the magnetic field is going into the page on the outside of the circle. So if we had a lot of different types of loops in a coil, like a solenoid, which could also be thought of as an induction coil, then in this particular case, we would have a much stronger magnetic field because each of these wires causes that magnetic field in there. Force on a moving charged particle. So basically, when a charged particle is not moving, there is no magnetic force. A charged particle only produces a magnetic field when it's in motion. Okay? And so if it's at rest, no magnetic field produced, and you don't have any magnetic force. Remember, for any sort of force, be it gravitational, electrical, or magnetic, you only get forces when you have two fields interact with each other. So for example, right now, you're on the Earth. You have mass, the Earth has mass. You have a gravitational interaction with the Earth, and you feel that force as your weight. The Earth actually feels that force also. You're pulling up on Earth with the same number of newtons that the Earth is pulling back on you. That's just Newton's third law. So the same way charges interact with each other and magnetic fields interact with each other. So the key thing is you only get a magnetic field from a charge when it's in motion relative to a particular frame of reference. This is the flat hand rule, which I like. If you remember, I slapped someone, I think, upside the face with this one. And so that actually is something that's super useful. And it deals with, you do have a charge going through a magnetic field, and you can predict the direction of force. So the direction of velocity of a positive charge is the direction of your thumb. That's same as we had in the curvy hand rule here. But now we would think of the direction of the permanent magnetic field as your fingers. So allergies, holy camole, fingers field, and then the face of your palm is basically the direction of the magnetic force. And in this case, that's out of the page. If you have a negative charge going through a magnetic field, everything's the same except you use your left hand. If you have something like this at an angle, what you would do is you would take the component of the magnetic field that's perpendicular to this. So for example, if this is a positive, it says it's an electron, so it's a negative charge, so I use my left hand. I point my thumb to the right, and my fingers, which represent the field, they're going up and to the right. But if I'm holding my hand flat, I can't point my fingers up and to the right easily. I'm going to just point them up because that's the component that's perpendicular. So this tells me that the force on the electron is into this page. Now, it's not going to be as much into the page as if the magnetic field were going straight up. This is a way to determine that amount. I don't think you're going to have to calculate that, but you might need to explain, hey, what happens to the force on a charge if now it ends up doing something that's not perpendicular? The other thing that's interesting is if you put a charge, gosh, I get my allergy medicine. Anyhow, but if you shoot a charge into a field, a permanent field, so let's say this field was straight up, what you would end up having happen is you'd end up having, actually I'm going to draw that here. So let's say these blue arrows are now the magnetic field. So when we have this charge go here, and pretend I've got a bunch more blue arrows over there, what you're going to end up doing is you're going to end up moving, that charge will move perpendicular. So initially at least, the force on that charge, if it's an electron, and I use my left-hand rule, is going to be into the page. But as it ends up going into the page, now the force is going to be directed to the left. And then it'll be out of the page, and then it'll be to the right. So it'll go in a kind of weird sort of circle. At any rate, that means that that's a centripetal force, no change in speed on this thing, because the force is always perpendicular to the motion. I think you should really go back, take a look at like I said, the active physics simulations we did, and I think we did a lot of conceptual questions related to this in your textbook. Well, let me check the chapter. It's going to be in the 20s. It is chapter, I think, 24. Yeah, 24. So take a look at the conceptual questions we did there. I probably had that as a handout, I'm thinking. Maybe 25 also, but definitely 24. All right, so moving along. Magnetic force on a wire. Okay, something like this. If you remember, we did that lab around Christmas time, which I think was a really good lab, and that would be a great thing for you to review, because I do think this is a fairly likely topic. Definitely something with electricity will be on your AP exam this year. Could be magnetism, could be circuits, could be capacitors, could be charge, stuff like that. All right, anyhow, with something like this, if you've got a wire and you've got a magnetic field here that's going from left to right, what you're going to end up having happen is if this current is coming out of the page and it's conventional current, you would end up having the magnetic field go around counterclockwise like this. So below here, you'd have two magnetic fields going the same direction. That would be an attractive force. Above the wire, you'd have two magnetic fields going the opposite, or pardon me, two magnetic fields down here going the same direction. That's a repulsive force. Two magnetic fields here going opposite direction. The permanent one going from left to right. The temporary one around the wire going from right to left up here. So you get a net force up. So I didn't say that very well, but I would read this. This is the formula you would use. Now the formula we had earlier, which was basically force on a wire, force on a charged particle, is Fm is equal to Q V times B. And that just means a cross product, which means you take the perpendicular components of it. So normally that just means multiplying them together. But anyhow, this is the same formula. Why is that the same formula? Again, taking a look at this, B is Tesla, L is length of a wire, I is current in amps, which are coulombs per second. So I get coulombs per second times meters times Tesla. Here, I get coulombs times velocity, which is meters per second, times this, which is Tesla. Coulomb meters per second Tesla up here, coulombs per second meters Tesla. Same thing. So this just takes into account that you have more moving charges when you have a wire. Again, pretty good here. Force between two wires is useful to think about. So if I look at this wire, If I have conventional current, then into the page here of my magnetic field, out of the page here. In this case, I would have caused by this A, I would actually have X's into the page caused by this thing if the current is going upward, and on the left side of the page I would have dots. So I don't know if I can do dots with this. Nope, I cannot. That did not do what I wanted to do. What? Oh, it did. Yeah, but it's not going to do it right. Anyhow, so you get the idea. So the dot's already over here. So in this area in between, which is where we're interested, the dots caused by this magnetic field interact with the X's from this magnetic field. That means they would attract. If this current was going downward, the dots would be on the right, X's on the left. Dots from this and dots from this means the two wires would repel. So this is the one I was talking about earlier, where if you have a charge go into a magnetic field perpendicularly, this is a little easier to see than the example I was given earlier. This force is always perpendicular. So here, this force would be acting upward. Then if I look over here, in this case, this force is acting to the left. If I go here, force is acting downward. So they should all be the same length. I don't know if I can do that very well. So you would get a centripetal force here, which is mv squared over r. You would also get that as the equal to the magnetic force, qvb. So one thing to remember, anytime you have a force pointing toward the center of an object moving in a circular path, it by definition is a centripetal force. And really all that is a fancy term for net force on an object going in a circular path. Could be caused by gravity, could be caused by magnetism, could be caused by friction. Kind of neat to think about. So technically the Earth's south magnetic pole is up here, north magnetic pole is down there. Even though compasses, the north pole points up there, which makes sense because north and south poles attract. Okay, so we have something like this going through here. We have an electron, mass spectrum. I don't want to worry about that. I don't think that's that important. I definitely don't think you're going to have to do those calculations, but this really does combine the mv squared over r and the fact that qvb. So when you do that, that says that the centripetal force is equal to a magnetic force. You get that the radius of the circle in this magnetic field, which would be like this, is mv over qb. So they could ask you things like, hey, what would happen to the radius of this if your mass tripled, if you were going faster, if the magnetic field strength was stronger? You could answer that, I think, pretty well using this combination of things. So moving through both magnetic and electric fields, they might try to pull something like this to try to get a bunch of different concepts into one question. So basically, you should know that the direction on a charge in a magnetic field, based on the prediction of how it's going to act, what we've just been talking about in this chapter, the force on a charge in an electric field is on positives, the force is in the same direction as the electric field, and negatives, the force is opposite. So in this case, if this were an electron, the force on the electron would be to the left, because electric field lines point from positive to negative. Oftentimes what they might do is they might ask you something like, hey, what direction should an electric field be pointing if you're given a charge moving through a magnetic field like this in order to get it to go in a straight line? So for example, if we go back here, this is going to initially curve up. So the question would be, if we want to balance that out at this spot and have a force downward on this proton, what direction will we have an electric field? Well, we would probably have an electric field pointing down. So since the magnetic force here is up, we would need a magnetic or an electric field pointing down. So the electric force on the proton would be down, the magnetic force at this point would be up, and it would go straight through. So you could think of that because then that field strength, electric field is force per charge, magnetic field strength oftentimes might be given to you, but you could work that out that if electric field is force over charge, force is equal to electric field strength times charge, and magnetic force is charge times V times B. So the interesting thing is, although whether the charge is positive or negative would have to be known to help you choose the direction of this electric field, the actual value of this charge itself doesn't particularly matter because it is involved both in determining the magnetic force and the electric force. I think I've talked kind of a lot about this stuff, so I'm going to let you read through some of these things. I will say with this, though, this last part, I do like this idea of things. So with flux, so I'm going to draw a circle here. It would be nice if it was not a solid circle. There we go. So if we have something like this, flux is basically field strength, magnetic field strength times area. So the area of a circle is pi r squared. Field strength you might have to know. So if I had something like this, if I have a circle and it's entering the field like this is, the flux is increasing coming out of the board toward you. So the big idea behind electromagnetic induction is it does not like that. It is like old people, like I say, and does not like things to change. In a way, this electromagnetic induction is like electrical inertia. So what ends up happening is you're going to induce a magnetic, an EMF or a voltage, and what you're going to end up doing is causing a current to flow that opposes the change in flux. So if we have a clockwise current here, if I use my right-hand rule, that means I would get X's in this region. Why? To oppose the increase in dots. Now if I move down here, it's not letting me do that, that's annoying. Nope, still not letting me do that. Okay, I'll do it again. So now if I'm down here, if I'm completely in the field, whether I'm moving or not, the flux isn't changing. No change in flux, no current. However, if this thing is now moving out of the field, and again, we'll draw that as an arrow going to the right, now the flux coming out of the page is decreasing. So what we would end up getting is a current that's clockwise. Why? Because, or pardon me, counterclockwise. Why? Because a counterclockwise current will induce more dots, and that would oppose the change of decreasing dots. So here, when entering the field, increasing dots, the induced EMF, which is a voltage, and the induced current produce a magnetic field that opposes that increase in dots. Here, when the flux is constant, no current. Here, when you're leaving the field, the flux is decreasing, so we're going to generate a current counterclockwise that would increase or oppose rather the decrease in current. So it'll be dots. I think these are some good, oh, there's where it did it. Oh. And again, remembering that something like this in here, in that region would have a much smaller flux than something with a bigger area. So the total flux depends on field strength and area. And I think that is plenty. I think you can talk about this, and I think there's things at the end of the chapter here, but I think that's really pretty good.